Good morning, everyone. Our next lesson in the probability distribution unit is actually what we call a geometric distribution. That's the technical term for it. In layman's terms, I call it waiting times. Okay, and you'll understand why I call it waiting times in a few moments. So, just as a mini recap, what have we done so far? We've discussed a probability distribution being a chart with all of the outcomes and all of the associated probabilities, and it helps us get the expected value. Then we talked about a Bernoulli distribution or Bernoulli trial, which means it's a probability distribution, but it's in the special case of only having two outcomes. And that gives us a beautiful special formula as well as a special formula for expected value. Okay, today we're going to open things up a little bit and we're going to talk about geometric distributions and in particular waiting times. So let's take a look at the start of the note and see what we've got here. It says, we've seen for Bernoulli trials, the formula is, and remember, let's go through it verbally, number of trials to number of successes, probability of success to the number of successes, probability of failure to the number of failures. And remember I had said to you, my preference is for you to memorize the formula in words rather than in letters. Now, never really pointed this out too much, okay, because we were more concerned with the formula and where the formula came from. But the important part of that particular formula is that you're measuring the probability of success. Okay, you're kind of thinking, geez, Ms. Martel, why are you impressing that upon us? Just keep it in your brain for me. Everything that we measured when we were doing a Bernoulli was in terms of the probability of success. So this tells us the probability of getting X successes out of N trials. Okay, let's take a look at an example. What is the probability of rolling 3 5s if you roll a die 20 times? So this is classic Bernoulli. 2 outcomes. A success is rolling a 5. A failure is anything other than a 5. And you could not do this by selection because it's happening 20 times. Remember, our selection questions sort of hit a max of 3 iterations. So the Bernoulli formula says the probability of rolling 3 5s, number of trials to the number of successes, probability of a success, that's rolling a 5, to the number of successes, probability of failure, anything other than a 5, to the number of failures. Very straightforward Bernoulli, very, very straightforward. It's the classic exactly question. Okay. The next logical question to ask ourselves is, how many times should I have to roll the die before a 5 would come up? So I've got the die in my hand, I'm rolling it, I'm rolling it, I'm rolling it, I'm rolling it. I'm writing down whatever, roll I have, I'm keeping track. How many times am I going to have to roll that thing before I actually get a 5? Maybe I could word that a little bit different. How long would I have to wait before I rolled a 5? How many rolls, how many iterations would have to occur before I actually got what I wanted. And this whole idea of how many times should I have to roll the die before getting the 5? How long do I have to wait before I get what I want? Is what we call a geometric distribution. And in layman's terms, waiting time. Now, here's where I want you to really clue in. The probability that you will experience X failures before getting a success. And this is extremely different, okay? I'm hoping you can see the whole note here. Give me a moment. A Bernoulli looks at the probability of a certain number of successes. A geometric, aka weighting, looks at the probability of a certain number of failures before you get what you want, before your success. And this is really key to the way your brain needs to work when you're doing these questions, and especially when you hit the day of the test and all the questions are mixed up. Okay? So I don't know, I'm gonna try to keep reiterating it, but that's the sheer difference. Bernoulli and basically everything we've ever done with probability is desired successes. Now all of a sudden, how many failures before I get what I want? Now, take a look at the formula. You're thinking, geez, this formula is short and sweet. It is. It's probability of success times probability of failure to the number of failures before your success. So probability of success times probability of failure to the number of failures before you reach your success. Okay, let me wait for you for a moment and then we'll flip. Again, please keep in mind, waiting times, geometric, measures the probability of how many failures before I reach my success. Okay, now let's talk about the top here. It says, note, there is no combination at the beginning of this distribution because there's only one way that our scenario can occur at the end of all the failures. So if you think back to the Bernoulli formula, notice the similarities and the differences between the Bernoulli and the waiting time formula. Combination, no combination. The reason there's no combination is there's only one way this is going to happen, a certain number of failures and then the success. Probability of success, probability of failures. Okay, so it's somewhat similar with a few little tweaks. Also, there's no exponent on the P. Did you notice that as well? On the probability of success, in Bernoulli, it's raised to the number of successes. In geometric, it's raised to the exponent 1. And why? Because there's only one way to have a success. Okay, so the two formulas are quite similar. Now let's take a look again at the similarities. Both geometric and binomial only have two outcomes, and they're repeated and identical. Or the repeated trials are identical and they're independent. So every trial is identical, rolling the dice, rolling the dice, rolling the dice, yet every trial is independent. Okay? So hold on, let me just write something down here for you, okay? I want you to really see the difference. The Bernoulli formula, number of trials to number of successes, probability of success to the number of successes, probability of failure to the number of failures. Geometric, absolutely no combination, because there's only one way for the scenario to happen when you have a success. Probability of success to the exponent 1, because again, there's only one success. Probability of failure to the number of failures. So the two formulas are very similar and their circumstances are similar. Two outcomes, repeated trials that are identical and independent. Now, we know for Bernoulli that Bernoulli has a beautiful expected value formula, and it looks like this. A nice quickie formula. Geometric is also going to have an expected value quickie formula, but I want you to take a look at the next statement because it's super important. With geometric, it's the expected number of failures before you get a success. And it's probability of failure over probability. So this is the expected number of failures before success. This is the expected number of successes. So what's really critical in this particular topic is the language again, guys. The language. Okay? What you're measuring. And it's just to be careful, and I'm going to show you exactly where you got to be careful. Okay. Let's start right from the beginning. What is the probability that the first 5 that you roll is on the 4th roll? Okay, so hold on. Let's do some rough work here. Roll 1. Failure. Roll 2. Failure. Roll 3. Failure. If I get my 5, roll 4, I get my 5, that's when I'm getting the success. That's what that question's asking you. What are the chances that you're actually going to roll a 5 on the 4th roll? That's what they want you to visualize. So probability of rolling a 5 on the 4th roll, probability of success times the probability of failure to the number of failures. Rolling a 5 is 1 over 6. Rolling anything other than a 5 is 5 over 6. Number of failures, how many failures did I have? 1, 2, 3. Calculator work, please. Roughly 10%. So the answer is that it's roughly going to be 10% that I'm going to roll my first 5 on the 4th roll. Very similar to the exactly. Okay, let's keep looking at the next example. Can we put a star beside this one? A little bit tougher. What is the probability of getting a 5 in the first 3 rolls? In the first 3 rolls. So, wait a minute. This comes to mind of some different scenarios. I could get a 5 in the first roll, or I could get a 5 in the second roll, which would mean get the 5 in the first roll. This would be failure, then the 5. Or what it could mean is failure, third roll. That's what that's asking you. What is the probability of getting a 5 in one of the first 3 rolls? So it could have happened in the first, it might have happened in the second, or it actually might have happened in the third. So that means I've got 3 iterations of the formula here. Probability of success, probability of failures to the number of failures. Now, if I'm getting a 5 in the first roll, That means I've had no failures. Probability of success, probability of failure, and if I'm getting a 5 in the second roll, that means I had a failure in the first roll, then got what I wanted. Probability of success, probability, I'm sorry, that should be a 6. I'm sure you guys were catching me on that. Probability of failure. And if I got what I was looking for on the third roll, that meant that I had failure, failure, success. Again, with these type of questions, your marks, the bulk of your marks are right here. Okay? The rest of the calculator work, my assumption is that you know how to work your calculator, and this is all going to be worth, you know, half a mark. So there's a 42% chance that you're going to get a 5 in the first 3 rolls. Not bad chance. Okay, let's flip when we're ready. Which roll would you expect to get the 5? So what this is saying is, how long should I plan to roll the dice before getting what I'm looking for? So this is my quickie formula of my expected value. Oops. Sorry, guys. Actually, I don't like that. Give me a moment. I want it to be perfect for you guys. Probability of failure divided by probability of success. Now, if I was to write that out, probability of failure divided by probability of success, and then I know when I'm dividing fractions, so which roll would you expect to have your first 5? Why am I hesitating? Why am I hesitating? Because, God, the math on this is easy. Why am I hesitating? Can I go back to the first note? Oh, I lied. Can I go back to this? The expected number of failures before you get a success. So this 5 is the expected number of failures before getting a success. So you're expecting 5 failures. So on what roll will you expect the success? Careful, careful, careful. So hold on, let's reiterate that. The expected value for a geometric, for a waiting time, measures the number of failures. So what this is telling me is that I failed, I failed, I failed, I failed, I failed. Boom, I got what I was looking for. So what is the expected roll that you're going to get what you wanted? Your 6th roll. Be really, really, really careful, because that therefore statement is worth a whole mark. Okay, be real careful. Okay, let's take a look. You roll a pair of dice. Oh, okay, we're familiar with this. That means dice chart. Give me a second. Oops. Got a little bit crazy there on my dice chart. Okay. You roll a pair of dice. What is the probability of getting your first, what is the probability that your first pair will occur on the third roll. Again, what this is saying to me is first roll, no pair. Second roll, no pair. Third roll, yep, get what I'm looking for. So failure, failure, success. Very classic. Geometric. Pair on third roll. And what's classic about it is that this is your exactly situation. Now, it doesn't say what pair I'm looking for, so in general, I'm probably looking for any of the pairs. So double ones, double twos, double threes, double fours, double fives, double sixes. So probability of success, that's getting a pair, 6 of them. Probability of failure, that's anything else that isn't highlighted. Number of failures. 12% probability. Okay, let's keep going. How many times would you expect to have to roll the dice in order to get your first double? Also, your first pair. A double or a pair is the same thing. Okay, so this is expected value, which says probability of failure over probability of success. 30 over 36 divided by 6 over 36. Change it to multiplication. Again, be super, super careful because this 5 represents the number of failures, and that's not what you're asking. How many times would you expect to have to roll the dice before you got your first pair? Therefore, 6 times. 5 failures, and on your 6th roll, you would get what you want. Hope you're seeing that clearly. What is the probability of getting a sum of 7? I'm going to have to go back to my dice chart. A sum of 7 in fewer than 3 rolls. Okay, so hold on. Let's talk about a sum of 7 first. Let's get that highlighted up top here. A sum of 7. One, two, three, 4, 5, 6. Okay, fewer than 3 rolls. Fewer than 3 rolls means that you might get your sum of 7 on the first roll, or you might get your sum of 7 on the second roll. Fewer than 3. Fewer than 3 is 1 or 2. Okay, probability of success times probability of failure to the number of failures. Well, if you're getting what you're looking for on the first roll, you lucked out. Probability of success to the probability of failure. If you're getting it on the second roll, you had 1 failure. And reiterating, I didn't go over the word or, but I think by this point in the game, we're all feeling good about that or. Okay, fantastic. Actually, guys, you know what? I think, if you don't mind, I'm going to omit the last example. This is one of these ones that it would be better off when we're in class. It would be a really hard one for me to do online like this. And it's not a big deal for the test or any assessments or any assignment. It's just a nice one that I like, kind of cool one that I like to do with you when I have you in person. Okay, so we're done. Thanks for today. Your homework is the handout, and full solutions are included. Talk to you soon. Bye-bye.